Okay, so let's go. So I've got a couple of little housekeeping notes from you to tell everyone. So tomorrow at 6 p.m, we've got Amy Chan coming for the Perspective seminar. I really recommend coming in person. Like, one of these things when I was young and didn't know what I was doing was I didn't understand how the world worked. And this big part of professional development is networking. It's one of the reasons I do this course, because I get to meet lots of young, smart people, and, you know, maybe you'll help me later on in life, because Brisbane's a small town. You meet the same people again and again and again and again. You know, so make sure you come up and make sure you ask lots of questions. Make sure these people know you. It's like, no, I always used to worry. I used to have this self-consciousness of like, oh, don't ask questions because I'll seem like an idiot. It's better to seem like an idiot because at least 10 people know you, honestly. Like, don't be shy. It's not worth it. Yeah, I come here, be an idiot. It's great. So yeah, so make sure you come, make sure you ask lots of questions, get to know people. I was like, as an example of this about networking, which is like one of these things, since my PhD, none of the jobs I've got, I actually applied for. It was people who knew me asking me, oh, Paul, would you like to come and work here? The last time, in my current job now, I was planning on taking a bit of time off to just like be lazy and do whatever I wanted. And nah, people come out of the woodwork, go, Paul, would you like to work here? Would you like to work there? Networking is super important, getting to know people. Please do it, you know, don't be shy. It's not worth it at all. Yeah, so Amy works at Polymathian, I think I said that, but she'll let you all know about it tomorrow. I'll turn up and Yoni will be there as well. But yeah, please come and ask lots of questions, make her feel welcome. It's a good thing that she's coming to do it. Okay, Wednesday, it's Brisbane ECA. There's a 6 p.m. Zoom practical by Tina, so that's still on. Recorded to Blackboard, but there's no 4 p.m. face-to-face practical. We've got the consultations on Wednesday at 7:30. It's been pretty sparse. So if you need help, or it doesn't have to be about anything, I'm there, Yoni's there, come and waste our time, because it's not wasting our time. Just any questions if you're having trouble, doesn't matter of level. Yep, feel free to turn up. Hopefully the single-digit homework questions are complete, or at least seriously attempted, if you want an idea of like where you should probably be, maybe. Use Ed as much as possible. Hopefully you've been finding that useful. I probably should be a bit more active on there. There's an additional special consultation hour on Thursday by Ivana in person, and half an hour by Yoni on Friday via Zoom. That's specifically for people who feel like they're struggling. So make use of that if you're having trouble. And information about the quiz will be released next week. And Yoni will do a Blackboard message to cover this. So if you missed anything, any ambiguity, you should send it there. Cool. Any questions about any of that stuff? No. Just, yeah, make sure you ask lots of questions. Make sure Amy knows that you are. That would be my only advice. So back to schedule-wise, we're into week 3. So we're going to get through most of Unit 2, hopefully today. I'll get started on the end bit of Unit 2. End of Unit 2 will be a little bit different. So I'm going to talk about Unix and some terminal instructions. If you've never seen that before, these arcane spells of moving around in directories and stuff and copying things. What Unix is about, you know, what an operating system is, maybe a little bit. I'll talk a bit about Git, and I'll talk a little bit about development environments. So why would you use something like VS Code? Why would you not just use Vim or something? That's the plan. I'm happy to take, if anyone needs, like, because those 3 parts and they're kind of logically distinct. If I'll probably only get started on one of those today, maybe, or maybe not, or maybe I might be stuck in the sorting bit still. If anyone has a really like I'm really struggling to get Git, say, please come and tell me in the break, and I'll talk about that today, because I'm happy to swap them around to the order I do them in. Or it doesn't matter, I'll just go through in the order they're in the notes. Okay, sound good? All right, section 2, algorithms, the brief review, started looking at terrible bubble sort, quadratic timing, you know, some empirical evidence that maybe it's scaling quadratically, then, you know, it's kind of obvious. If you're leaping through, remember bubble sort, swoop through, anything in the wrong order, switch them around, get to the end, that's not going to be sorted, go through, switch them again, switch them again. Just by that sort of, it's like that double loop structure of going for I in 1 to n-1, for j in 1 to n-1. If they're the wrong way around, switch them around. That, you know, hopefully that's obvious. Just count up how many of this rate limiting step are going to happen. You're going to get quadratic. The scale's quadratically with the size of the problem, which is not great. Things get worse than that in general. We talked a little bit about, you know, these are the different scalings. You can get worse, you know, you can get factorial, which is kind of the worst you'd expect to see, but there's a large class of useful problems that scale that way. N log n is the best you can do for arbitrary data. Can do better with special types of data, but n log n is what you'd be hoping to see. And it looks like the built-in sort does this, and this is all part of your homework. I meant to check homework exactly what you were going to do for that. But you know, if you want to look at what Julia does, this is the thing. You can open source languages are great. Everything's online. But, you know, if you really want to go through and see how sorting is implemented in Julia, in one of these ones where a lot of very smart people have tried to make it very fast, you can go and do that. Not necessarily the best idea for getting an idea about how it works, because optimized code is not necessarily the most readable code, but Julia is pretty good. Okay, that's what we're going to do. So, okay, that's like basics of bubble sort, scales quadratically, probably can do better. N log n, if you do the theories, like kind of the best you can do. Can we come up with an algorithm that is n log n? One of the ways to approach that is to look at data structures, and data structures can help you get better performance. I started by talking about, so there's kind of these two parts. There's like, you know, clever algorithms, clever data structures. Best of the world of both is like clever algorithms and clever data structures. Because if you have a clever data structure, you kind of get the performance for free. It's like just the way the data is laid out, you can do nothing basically. And we'll give you an example of that, but we've got to build up to that. So, cool. First is arrays. You've seen arrays to death. Introduce this concept of like a pointer. Don't need to know this for Julia. This is kind of like just to show you what's going on, you know, how sausages get made. Down at a low level, you can see how these things point to an address in memory where the actual data is. Yeah, saying, you know, if you want to get into this stuff, if you find it interesting, you can look at datastructures.jl is a really useful module. Used to be part of base Julia. I'm not sure if it is anymore. I don't know if that would be like, I don't know if you have to do package add to get data structures. Maybe you do these days because they tried to take everything out of base Julia. So there's all, you go through here, there's a bunch of stuff, more than you'd ever want to know. Or if you're into it, you'd want to know all of them and know them backwards and forwards. You know, because this is such a useful thing for when you're programming, to know a few basic data structures. So array is kind of the basic one where it's just like there's a list and there's an order to this list. You can think of it as a mathematician, kind of like a vector. That's okay. Then I finished on multi-dimensional arrays. Okay, so this is basically like the big point here, I guess, the teaching point is that how this is laid out in memory has effects. You can't just, you know, even though access into an array is order 1, it depends on how it's laid out in memory. So there's a particular stride direction that will make it faster or slower. And I have definitely run into this one in my professional career, where the way you lay out multi-dimensional arrays will be important for getting performance benefits, particularly if you're going like, not so common, but, you know, matrix is pretty common, and you're going to go this 3, you know, a tensor or some higher order thing. Like if you're doing tensor stuff, like some of you will go off and do that sort of thing in mathematics. You know, if you're laying out tensors, how you're going to access these things will matter even more than they do for these 2-dimensional arrays, because they'll be even further apart. And yeah, so basically the idea is things that are close in memory, access is faster. We did a little demo of that, that if you sum over the rows or you sum over the columns, so that's basically the only difference between these two codes. We're going ij, the ith and the jth element, is the fast bit on the inside or the outside. And if you do that for a fairly misshapen array, so this is 500 by 1,000,000, you'll get 10 times difference in whether you sum over the rows or sum over the columns in speed. So that's non-negligible. That's quite a big difference. What am I trying to get at with that? It's just like sometimes low-level details matter. This is one of these ones. Please keep it in mind. Not super important, but interesting to know how these things work. They're not, I guess it's this point I'm going to try and keep ramming it down your throats, is that like, it's not really a matrix. It's not really a vector. How it's implemented on the computer makes a difference. They're not really real numbers. They're floating point numbers. They're not really integers. They're at a certain level of precision. The details matter because sometimes the details have a difference when you're implementing these things. Always happens, always happens. And this is this idea of data structures in general. It's like how you lay these things out may or may not make your problem easier or harder. Most of that's to do with speed and scaling. Okay, I think I'm up, so it's a bit longer than I meant to go, but that's okay. Good to review, because sometimes you get lost on these things. Okay, so I'm going to start with an idea of a dictionary. This is like the next, after an array, you have this thing of like, I kind of want to say start with sets first, but dictionaries, sets, we'll talk about sets after dictionaries. Dictionaries first. There's a few interesting things. There's this really useful idea that like, you know, it's this typical nasty pattern of like, you have an array and you know, I want to get the 6th element to get the data out. And it's like, well, maybe that 6th element, the order really isn't important for my problem. I've just put it in an array because it was easy. So like, yeah, that's really common. So maybe you want something that's more like, I have a key and I have a value. For each key, there's a value and I want a mapping to that. So I don't really care about the order in some cases. So the natural thing for this, and so that's why I was kind of like saying, like dictionaries and sets are like close friends. So a set is much more natural. So like the difference between a vector and a set, I hope that's clear to everyone, that, you know, a vector, 1, 2, 3, 4 have order, whereas a set's just a bag of stuff. And you just mostly want to know if something's in the bag of stuff, not whether, you know, and the size of it, you know, those sorts of things. But there's no natural order to the elements in the set. So, you know, like sorting an array makes a lot of sense. Sorting a set, it's like, oh, that's kind of a bit weird. It's like you probably weren't really ever dealing with the set in the first place if you think you want an order on top of it. So that's a set. Then you go, well, as soon as you have a set, you go like, well, there might be some things attached to the things in the set. Like if I've got like the set of students in Math 2504, they will have some attributes attached to them, like they might have a student number, they might have blah and blah and blah. This idea of attaching things to a key, so the key would be the student name, the information would be the values. So this is the idea of a dictionary. It's a data structure where checking whether something's has a key in the collection is really fast, like it is accessing an element in an array, and then you can get the values. So has anyone dealt with, who hasn't seen a dictionary before in another programming language? Is this a new concept? Got a couple of people, so that's good. So I'll go a bit slow just because it's super useful. If you've seen it before, like this will be nothing new to you. I guess I'll make it a little bit more interesting for people who've done it before, but yeah, I'll try and draw a connection of like to design of programs and like data modeling. Because this is like, it's kind of like, I think it's one of these things that's a bit like art, which is annoying because it's hard to teach, but you have to see it a few times to understand, like, why would I choose a dictionary for this problem? Why would I choose an array for this problem? Why would I choose to do structs in the language? So I showed an example of how to set up a Julia struct really quickly last time, but I didn't want to introduce it too much because it's in module 4. But you've got these layers of things you might want to care about. So dictionary is really easy to interact with. You know, if you want to make a dictionary, you just say dict, and then you're going to go the types. So string. And then you're going to say, this is the type of the keys. And the second one in this thing is the type of the values. So you might want to go, these are ints. And then that will make an empty dictionary if I just put string and int and brackets. That will initialize an empty dictionary. So there's no keys or values in it to start with. Because it's Julia, you know, if you don't know what these things are going to be, you can do that too. If you don't know what type they're going to be, like say you're reading a JSON file, they'll typically come in with any, and you have to know something about the schema of the data to work out what types they are. But, you know, we've got some dict. We can add a key by square brackets, and we'll just go call and an int. So this will be student name to postcode. I live way out in the sticks. People were talking about the Ekka holidays being on Wednesday. I don't even live in Brisbane. I live in Moreton Bay. So I went to the Ekka with my kids today. That was terrible. I was terrified of getting coronavirus. And then I had a Dagwood dog, and then I had regret. Seems like a normal experience. So forgive me if anyway, so I live way out in the sticks. But, you know, so now I've got a dictionary. It's got one key in it. We can add another key. I don't know, Mary lives in CBD some reason. It's too much money. Okay, so we have, you know, Paul, Mary. One of the ways to interact with this is you get the keys of the dictionary. So that will give you the keys, and then you can go values. There you go. If you want to iterate through this thing for key value in dict, show key. Okay, so you can iterate through these things. The iteration order, though, is arbitrary. So like I was saying, with an array, there's a particular order. With the dictionaries, you get no guarantee about the order things are going to come out. It's more just these things are in there and they have these values attached to them. So the difference is, though, like we were talking about sorting, and like, you know, for an array, like it's an equivalent problem to wanting to sort an array. It's like, do we want to check if a thing is in an array? It's like, I hope you can see that that's really a very similar problem to sorting. You've got to go through, check if the thing's in there. If they're, depending on the type of the thing, like you might be able to cut it down a little bit. But what's really fast about dictionaries is checking whether a key is in there. Like the whole implementation is about accessing keys, getting the value is really fast. So, but there's no natural order to how things are in there. That's the thing to take away. That's the basic interactions you do with a dictionary. So again, that little setup bit, to initialize an empty dictionary, you can have this slightly funny syntax. You can go, it's another way to do it. To make a dictionary, it's a bit funny, but that's another way you can initialize these things. So it's kind of easy to do the empty dictionary when you're dealing with these types and then pop them in as you get them. Another thing you can do with a dictionary, we had this dict. If I try and get a key that's not in there, it'll throw an error. So key error Tom not found. Oh, hey. That name was in my head for a reason. So another way, that's like, now you have this problem practically, talking about software stuff, is like, you have a dictionary and there's a key that may or may not be in there and you want tests, like you don't really want it throwing. So a question from on the chat was, why the parentheses at the end of the initialization? That's the way to get it with an empty So these two, just Julia syntax. So these two in the curly brackets are the types, and this is an empty array. You can do the same with arrays. So you can go like an array of type float 64. That will make an empty array. It's just Julia syntax. So that's an array of dimension 1 type float 64 with nothing in it. Similarly for a dictionary, that's the dictionary version of it. Sorry, just saw the question in the chat, thought I should answer that because it seems important. So now you got this problem of like, you know, with an array, you know its size. So you can do this iteration thing. And I showed you the nasty trick of like doing inbounds if you want to make it fast. For dictionaries, it's not so obvious whether a key is actually going to be in there or not rather than testing it. So the way you end up writing code like this, it will be like has key, no, can't type. So you get this function has key, it's false. So you'd write this loop that goes, if has key dict Tom do something, otherwise carry on and do something else. Another option is you can use the get function. If you know like, oh, Tom's going to be there. If Tom's not there, give me nothing. So this is a bit like a little funny ternary thing where you're going to go like the variable, the key, and what value you put in there if it wasn't in the dictionary. So depending on your code, you might want to do a special thing. You might have a special default value that it should drop into. That would be the type of thing you're doing. So nothing's a thing, or maybe you want 0. So like say you're summing up people's incomes in a dictionary and you're going to go like, here's a list of people that might be in a subset where a subset of these might be in the dictionary, go through. I'm going to sum 0 if they're not in the dictionary because they don't have an income. Blah, blah, blah. Okay. Cool. That's the interacting with it in Julia. I hope that was clear. It's pretty simple. So you saw initialization. It's pretty easy. This funny signature of this is the type. These are the subtypes with the key and the value, empty dictionary. And working with it, how to put values in, how to get values out, how to test whether a key exists, how to, and how to get a value with a default, how to get something from the dictionary with a default. Again, you know, always look up the help. So you'll see this funny thing, it will say constructs a hash table. So these dictionaries have names in different languages. I call it a hash map or a hash table or a dictionary. That's partly to do with the implementation of how you do the keys, like how you do this key test stuff. So this is like hash table or a hash function is a super useful, interesting thing in computer science. I'm going to talk a tiny bit about it. I think it's interesting. It'll come back up again, the idea of a hash function. They're used in cryptography. They're used in Git. So when we start talking about Git, you'll see there's little shards, they're called. There's little random strings that to do with the commit you did in Git. That's actually passing your code through a cryptographic hash function. That's the output of it. That's what you'll see in Git, those funny little strings. This is to do with the implementation. I think we've got, there's many ways you can implement a hash map, these hash functions. If it's an array, you can do the nasty thing. You can go like, number 1 is 7, number 2 is 3. You know, you can just use an array to implement a dictionary. And sometimes that's a really useful thing to do because it'll be faster. Even though it's order 1 to do this, key lookup into a dictionary, it's also order 1 to do it into an array. The difference in time is huge because you're actually passing it through a complicated function in the dictionary case. So, sometimes plain arrays are much faster. But, sometimes you don't know the size and sometimes you don't know how much stuff's going to turn up. So then dictionary is a much more flexible case. So we've got a really naive array-based implementation of a dictionary here. So I don't know how much to say. So we've got we've got a bunch of keys. There's an array of strings, undef naught, dictionary values, an array of int16s, undef naught. So that's initializing empty arrays. So what the idea of this example is like we can just do this stuff with arrays. And hopefully you can see why that's silly. In a particular case, it might not be that silly. But again, it's this idea of thinking about the complexity of implementations. So if we have an array, let's just copy some of this stuff across. I'll just make it so I can push dict values. So we've got this function, add key value pair. So you've got keys, values, new key, new value. Because this is an array, keys and values in this case, dictionary keys, dictionary values, we're going to use the push operation for an array. So empty, I'll do that as a string. So again, alternative, can't use the same overload. I got an error because I was trying to use keys, but I can't. I'm not allowed. It's a special one. I'm not allowed to overwrite keys. Dictionary keys is an array of strings. If I push to an array, have I shown you this before? Push, everyone's seen push? I'll just do it again, but you should know what it does. I can't spell. Push, dict, keys, A. It'll just push a new key. So if we had a new key pair, that's basically all it's doing. It's like it's going to push it into the array. And because they're pushed in, push is deterministic in the order it comes into the array, they're going to be in the same spot. So if you want to find the value of a key, you just have to search through the array of keys for that value and then find the index and then get it out of the other array, which is this kind of nasty pattern I was saying is like, you don't want to do. You go through the keys. If it equals, this is one way of searching. I'm sure you guys could come up with another. You're going to enumerate the list of keys. And then if the key is equal to the question answer, return the value at I. So that would be like, this is a super naive implementation of a dictionary. Otherwise, error, couldn't find the key, which is kind of like the way the dictionaries one was implemented. Hopefully that's clear, that function. Yeah, again, you can see that the time complexity of this, when we go on to test the value of a key, you got to go through every element of the array and check whether it's in there. So straight away, hopefully you'll be able to see it's order n. It's to do as many keys as you have. This thing's going to take longer and longer and longer to do. Yeah, that's not really what you want. So what you really want is fast lookup. So the implementation is usually via a hash table. I'm not going to say too much now, but again, when I talk about Git, I'll talk about this idea of a hash function. It's also really useful when you think about random number generation. So all these things and computational, I guess, information theory, this link between how complex something is versus how random it is and whether you can deterministically generate random numbers. This is like something I find super fascinating and there's not really a good answer for. So I'll just drop hints about it so you can go off and read about it because it's super interesting. It's basically, you guys, part of one of the later modules, you're going to implement a random number generator. And hopefully this is a very strange idea to you because it does seem like a strange thing. It's like, if I'm gonna have a function and I take something in and I can basically make a random number generator out, that's a very, very strange thing to be able to do. And it's not 100% clear to me whether that's possible in general to do that, to make something that's completely random via deterministic means. It's kind of odd. It's kind of odd. But we base a lot of stuff off it. We base cryptography off of it. This idea of a hash function is like one of these implementations. Basically, the idea is like, I just wave my hands really quickly and I don't want to say too much about it, but like you pass your key through a function that's going to make like a random address in memory and then you put your stuff in there. That's the idea of a hash table. You're not necessarily these different applications I talked about where it's like, you know, cryptography, where you want to pass like a secret message and you can like, whether when I go to download something on the internet, I want to verify whether the file I downloaded is the same as what the developer who made it intended it to be. It's a really useful thing, right? Like, so nobody put secret viruses in your code in the binary you downloaded off the internet. You want to pass it through a function that'll go like, okay, take this thing, make something that's like, here's a discriminator for this file, this random string, and I can just check that. He or she ran it at their end, I downloaded it, I run it at my end. If we get the same string, I can be pretty sure that we downloaded the same thing. Same with this is like the idea of a hash map for a dictionary is like I can take the key, points to a random address in memory. If I get another key, it's not going to point to the same address in memory. I just say really quickly that it really, because you've got like this performance concern, it's not necessarily guaranteed that you're not going to get hash collisions, they're called, where two keys end up pointing to the same bit of memory and then you have to do something. So they're not really order one when you're doing a dictionary. They're kind of order one. Sometimes they're not. So the analysis of the complexity of checking whether a key is in a dictionary is like, yeah, it's kind of order one. Most of the time it's order one. If you get really big, it's going to be a problem. If you've got a really huge dictionary, you got to deal with it. There's many, many ways you can do it though. It's like one of the things I thought I might talk to you about, but I won't, is the idea of like a Bloom filter. Is like you can have these other data structures that are checking whether a thing is in a list, but you have an approximate guarantee. This is something they actually use in web browsers for like whitelisting ranges of internet addresses that you're allowed to go to. So like there might be some naughty one that you go to type it in and it's like, no, that's just full of viruses and you're going to be in trouble. You can't really send the query out, do a search, is it in this list, send it back and have that implementation be efficient. So they use this idea of like a probabilistic check this is probably not in this list, so it's okay. Go off and read about Bloom filters, it's really interesting. Hash maps too. This is like basically the idea. So the best friend of a dictionary is a set. So I talked about these, you know, I wanted to talk about sets first, but you sort of like, it's really natural to want to talk about dictionaries because you go like, I got this key and then I got a bunch of other stuff. But, you know, as a mathematician, you're super interested in sets. And basically you can just say, if it's in the set, like you can just have a dictionary with keys and no values, voila, that's a set. So in terms of implementation, it's just like you just have a bunch of keys. Use the same machinery underneath and go like, just a bit for dealing with the keys and whether they exist or not in the list, and call that a set. Underneath, they're basically the same implementation. So this one should be useful for you, maybe. I don't know, particular homework questions, you may want to check whether something is in a list of stuff you already knew about. A set is a good data structure for doing this without having necessarily a value attached to it. So say you've got a list of things that you're going like, I'm going to generate this list and then I've got to test whether a thing is in this list of stuff I've come up with already. Good thing is a set. So set is, so property of a set, if I put the same thing in a set, does it end up with a copy in there or what happens? What happens to sets? One of each. Same with the dictionary. So I should have said that. So if you look at this implementation based on arrays, did anyone notice that bug, or was it all moving too fast for anyone to notice? There's no deduplication of keys in this implementation of sets via arrays. So really you should be checking when you insert a new key, does it already exist in there? Otherwise you have an ambiguity of like, this key is actually in this thing twice and it has two values. That breaks everything. So it's probably even slower to do this thing properly, like this naive implementation. What you should be doing is when you're adding a key, you should find whether it's in the list anyway. You know, you can't just push them in there. And when you go and check whether a value's in there, you've got to loop through them all as well. So that's why doing it with arrays is bad. So yeah, dictionary is the same. It's like you add the same key twice, it sort of obliterates the key that was in there before, something to watch for. But if you know you know, if it's actually a set, like if you're talking about the set of, say, prime numbers, you know, that's a data structure you might want to use. You know, you put the thing in there once, it's only ever in there once. You don't have to worry about it again. So you have the usual set operations. So we got A, B, omega, some bigger set. And again, you notice this thing about like there's no particular ordering to these things. You notice as it comes in, I'm putting it in 2, 7, 2, 3. It comes out 7, 2, 3. There is no order to sets, right? They're a set. You don't care about the order. If you wanted an array, use an array. But if it's about whether something exists in a set or not, use a set. Model, they're usually for these mathematical type objects, there will be an object that corresponds one-to-one. So use the right one for your problem. I'll say it again and again. Okay. So you can do all the usual set stuff. You can do union of A and B. Again, not counting duplicates twice. You can do intersect A, B. So there's only 2 and 3. You can do, it's going to be called something. So if we know the difference, set diff. I'm going to struggle to remember the actual set notation stuff for this. It's like a minus, I think, from memory. You guys would have done it more recently than me. And if you want to do the complement, which is like the difference between the universe, you can do all this and the set. Set diff has a side. Oh, that depends, yeah. So if you want to do all those things, they're all there. Okay. So the real big one though is like in. So you can do, so there's lots of stuff. So there's some collection. So this will work for a whole bunch of different types of collections, this function in. So if in item collection bool, so in, so we'll go to 7, A. It's true. 27, not true. This is like a really useful test. But you can also do it for an array. I can go A equals 1, 2, 3, 4, 5, 6, 7. In 7, A. It's true. 27 false. You can do the same thing, but there is a, this is like Julia magic. Oh, yeah, yeah. So good question on the chat. I'll come back to that in a second. Yeah, so in is a really useful test, but there's a performance consequence to the different data types. Again, checking whether a key is in a set, in a dictionary, or checking whether a value is in a set. Probably most of the time order 1. Checking whether a value is in an array is kind of like you got to scan through the array and work it out. Yeah, I think that's where I wanted to go. And I had a question on the chat. It says, it seems like it's not random. So random in quotes, definitely. So they came out in the same order on their computer as my computer. So, you know, the way the keys, it's not actually random. There's an algorithm generating the way these keys going to set. Not guaranteed between versions of Julia, and not guaranteed if you serialize the data. So save it to a file, bring it back in. You're not guaranteed to get these things in the same order, so just watch it. Not guaranteed to be the same between different versions of Julia even. So good luck. Don't rely on that ordering is what I'm trying to get at for dictionaries and sets. There is no guarantee to the ordering. Okay. So we've got a little timing exercise here. I think this is just to belabor this point. Look up an arbitrary number in a set. Yeah, so doing it in an array, basically this is like, we're going to check whether something's in an array and check whether something's in a set. You see that the set version of it's super fast compared to that. So it's this order 1 lookup for membership of a set. Okay. Who can think of a way to make the array one quicker? Is anyone paying attention and can think of a way that we could make checking whether something's in an array faster? This guy?
If we know the array is sorted, you can kind of like do a binary search.
Yeah, that's exactly right. So if like this is coming to the next bit, that's why I'm saying it now. If you're careful about how you insert values into your array, so I've got an empty array, I'm going to put the first new thing into this array. I'm guaranteed that that's in order. Fine. When I go to put the second value in, I can just test whether this is bigger or smaller than the first value. If I can insert this into the array in a particular spot, like in front or behind, sweet, that's fine. Then I know the array is still sorted. When I go to look at it again, if I want the smallest value or the largest value, it's order 1. I know which one's going to be the biggest or smallest. Searching, I can do like a binary search, some bisection thing to be really fast and go like, oh yeah, check in the middle. Is it bigger or smaller than the middle? Check, 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 really fast. This is that's a super important idea. You're going to have a problem probably with allocation of memory, practically implementing that thing. So there's a consequence to doing this thing, but you're going to be, again, you can make insertion a little bit faster, you know, rather than having to scan through the array and checking whether value's in there. Because we had that problem with the implementation we have in the lecture notes. You can get to whether the thing is really quick by doing one of these like cut things and get to the right spot. And you can do the same thing on the way out if you want to know, you know, hopefully that's clear. We're going to talk a little bit about a priority queue and a heap. So this data structure is very useful data structure again, and it's going to come up in your lectures again. So you're going to talk about this again. I think you're going to implement it yourself in Unit 5. So yeah, I've implemented a heap. I've definitely done a priority queue at one of my previous jobs. Basically, the engine of what we did was a big, scary priority queue. And the most common way to implement that is via a thing called a heap. A heap is very similar to this idea of an array that you always keep sorted, kind of, wave your hands. The idea is that you always know what the smallest value or the biggest, depending on which way you implement it, you always know what the smallest or the biggest value is going to be, and you can always get at that really quickly. And inserting a new value into the array with a new priority is really fast. And then you can go through things. If you want to come out in a particular order, this is this idea of a heap. Wiki page on heap, you can go and read. You're going to implement it yourself. I won't say too much about it, but you get this idea of like, you could do something like a sorted array. That's going to be fast. Here's a better thing for this particular problem of sorting. And definitely for things like if you're doing, anyone done discrete event simulation? Is that a thing that's come up for anyone? Anyone done operations research? Maybe you will. Priority queues are basically the backbone of discrete event simulation. So basically the idea that you're going to simulate things in time order. So what's coming next in time in a simulation, and you want to do that really fast. You have a heap data structure in the back. All these events, they get inserted into this priority queue, the heap underneath, and you pop them out in what's going to happen next time. Okay. So we've got a little bit of a setup that's like very coronavirusy because it was written last year. There's a vaccination clinic, and you're going to go, you want to make a queue of like, everyone's got a name and they receive a priority number that's a float 32. And the priority is a function of their age, occupation, and their medical condition. This is pretty similar to what I was doing in the past when I talked about this one. It's like, you have this arbitrary complicated priority. New person turns up, you got to put them in the queue in the right spot, and you want to pull off the queue who's coming next. There's basically, when you're trying to implement this simulation type, there's a couple of basic operations you want to going to do. You're going to add individuals to the queue, so to the priority queue. So this can happen at any old time. You don't know how many are going to come as well. So this is like a really natural problem. It's like telephone calls to a call center, all these kinds of things happen like this, where you're going to go, I'm going to add things to the queue, and I don't know how many. and I want to update their priority really quickly. I don't want that step to be slow. I want to remove the next one with the highest priority. This is my, and I want to modify priorities. So like if something might change during the simulation that modifies one of the priorities for any element in the queue, I want to be able to do that too. So that's kind of like the design goal of a priority queue. And a heap does this really naturally. Heaps also, this is one of your other guest lecturers, someone's going to do vehicle routing. One of the things you use a heap data structure for, is for searching for shortest paths on a graph. So like if you've got, you know, the typical Google Maps thing, where I'm going to drive from my home to St. Lucia, I've got all these roads in between and I want to find the path that's probably the shortest. You can actually use a heap for solving that problem too, as a data structure underneath. Shortest path problem, you use a heap. Is one of the ways you can implement this. Okay, so that's the thing. So these operations, a little bit of syntax stuff here. And this is going back to, so I feel like I need a better story around all this stuff, but it's getting close to the break time. Another thing you might want to do that's kind of like data modeling problem is sometimes you want to name tuple. So there's a little bit of another data model thing. So you could do this with a dictionary. Sometimes it's useful to do this with a dictionary. Sometimes it's useful to do it with something a little bit more lightweight. So if we've got elements and they're going to go into a priority queue, you could have a dictionary, you could have a Julia struct, you could have a name tuple. Sometimes you want to do one, sometimes you want to do the other. When you're starting programming, it's really kind of confusing about when you'd use one and when you'd use the other. My general advice is, particularly for people who are probably more advanced, is like, there's this, when you start learning about types and stuff, you tend to go a bit type crazy and everything's a type and you want to do the data model of everything. And the usual problem is you get the data model wrong. Like you spend a lot of time in design and you get the data model very, very wrong. So going straight to structs is usually a bad idea. What I usually do is I usually use dictionaries to start with. And I go like, well, this is very flexible. I can add keys and take them away. Then I might do something like a name tuple, or I might just go straight to a struct. It's probably for people who are a bit more further ahead with their software stuff, but I just thought it's useful to talk about. You'll see this stuff is like, you can have a name tuple, person A. It's another way, another data structure of modeling. They've got a name and they've got a priority now. You can make this really simple, lightweight way. You can make an array of these things, or you can make a heap out of these things. It's fine. That's a name tuple. We see the type of this. It'll say it's a name tuple, and it gives you the names as symbols. So this little other bit of Julia syntax we'll see is a symbol. So hi. Don't worry too much about symbols, but like a pro tip, when you're implementing dictionaries, another one of these consequences, if you use symbols rather than strings, it's actually a lot faster because of the way Julia works. Don't worry about that. But it's just like another little name thing. So you can see the type of that, and you can get their name and their priority. So this is just like a little simple thing. It's like another step up from a dictionary. It's better if you've got like static data, like you're going to make this thing, it's never going to change. Like you have both options come up. This is all module 4 stuff. Andy's going to talk to you about this stuff much more. I just thought it's better to show you early so we can do it. Getting up to 10.2. It's like a convenient thing. I think I'll do this after the break. We're going to have, yeah, I think that's a good time to break. So we just talked a little bit about name tuples. Don't worry too much about it. It's just a little bit of syntax. Sometimes it's nice. Dictionaries, stay with dictionaries for now. I'll just take a break for 10 minutes. Okay.
Dude, that's so cool. Yeah, I'm trying to think of you. I got a channel like about like 15 seconds, and now it's like 3.5, so I've like cut it down like that. I do like that. Yeah, sorry. I think the biggest slowdown is just writing the number of pairs. Yeah. And I don't know how to avoid going fast. I think about it, 28 is I think the other ones, I had the problem. I think which one is it called? 6. I shouldn't say that. It's like not expected to be able to do that. No, but like, is there any secrets to getting writing quicker, or is it just reducing the number of forms? So it's reducing the number of forms. Yeah. Depends how dirty it is. There's a way to I guess think about like same stuff with the book. So not doing really but number one thing we have unusually. Okay. Think about it that way. It's like often the thing works, things like that, the way to do that. Like if you're iterating over one thing on it, maybe just well, actually have to get those that way. Wrong. Then there's a whole bunch of software. So so get down to that when we're using Gradle. Oh, okay. Yeah. Okay, so that might be managed. There's an empty thread in this. You would have to start with this session. No, it's- Shouldn't be fun. Yes. Definitely,
Okay, back to it. Getting harassed with work emails while I'm here. It's hilarious. Right. Okay. So a little bit of a digression. Name tuples. I sort of want to say it so people are thinking about it. Dictionary, super flexible. Struct. I showed you that last time. This is like I could have made. I'll just say it. I'll just do it more. This is a thing you can make if you actually want to make your own custom data type in Julia. This comes up in module 4, but I'll show it to you a few times, so it's not a surprise when you get to it. You can do my priority 2, and you can have the same things. You could have this as a float 32, and name string. Put some tabs in there just so it looks a little bit cleaner. You know, if you really want to go there, you know, this is a thing you can do. Yeah, you can make your own priority. This is less flexible. So this is actually immutable. When you make a struct this way in Julia, it's like something you can't change. Once you got it there, it's done. You can actually make a mutable struct. You give it this. My priority 3. That's the thing. This comes up in section 4. I just want to show it to you now. If you don't want to go to all that effort, you can do a name tuple. If you want to go to even less effort and have more flexibility, just go with the dictionary. Data modeling is not easy. Like it's the most common thing that people get wrong when they're doing software engineering in general. So just want to say it. If it's not obvious how you set up a problem, it's because it's not obvious to anyone. And like all these giant companies, like a lot of the time what they're doing is like fixing up a data model that they made when they were in the startup days and they're stuck with it and they can't get rid of it. Typical thing when you go work in a place. Once that thing's in there and it's in through too much of the code, it gets really hard to change. So like data modeling is not a simple thing. Maths is kind of nice, right? Like we've had very smart people thinking for hundreds of years about what the types of these things are. You know, you have these basic things like sets and arrays, and vectors and matrices, and people have thought really hard about what they actually are. Not so much when you get out and you're trying to model like a business or, you know, some boring everyday problem, I guess. I don't want to say boring, it sounds dismissive because it is interesting. Cool. All right. So name tuples, structs, dictionaries, they're just stuff that's coming in. So this is a naive example of a priority queue, and it's naive because it's using an array. Same as the implementation of a dictionary above was naive because it's using an array. An array is a really easy, flexible data type, not always the right thing to do. So the way, as before, you know, like I said, you can do this array syntax. Let's make it a bit bigger so you can see. So this bit at the front is the type of the elements of the array. It's a name tuple with the two named elements of priority and name, and they're a float 64 and a string. So all that stuff at the front is just the type signature for this array. Same as we would do equals array of string. You know, string looks a lot easier. This is just a name tuple. So you got a little bit more overhead in your setup. Okay, so it's naive because it's an array. We're going to put things into this array and take them out in priority order, show that it's slow. Don't use an array. Maybe there's a better data type. So we've got a new person. They're going to turn up in the queue. And again, we're just going to push, same as this sorting example. So if we push, I always do a 1 for that. It's terrible. So naive priority queue, new person. There's a new person in the queue. Then there's yet another person, priority 23. Their name is Kim. I struggle to come up with names when I'm doing this stuff. Okay, so we've got an array. Oh, I pushed new person in there twice. Sorry. So again, this is this problem of like, if you're using arrays, you've got to check for duplication. Again, you don't want the same thing to happen twice. If they're already in the queue, they're already in the queue. You want to modify, not add a new element. So be careful. This is like showing you bad code so you don't write bad code. I don't know if that actually works. I probably should show you good code so you have an example, but that's too hard. So show you bad code, you can work out how to make it good. So we've got a bunch of people. And again, if someone, we're talking about these things, we had this desiderata of things we want to do with this queue. We want to add and remove individuals from the queue. Remove the individual with the highest priority and modify an individual's priority. Useful function again is this delete at. So if you have an array and you want to delete a particular element of the array, it's this delete at function. If you can spell, delete at. So you have an array and you have a range of, you can give an array of indices or just a particular index, both are fine. So I had my stupid, I pushed the same thing twice. So if I want to get rid of the first one, no priority queue, I added Yarden twice, there we go. Then the priority queue's only got 2 people in now. So the problem is if we want to get the highest priority or the lowest priority one, we've got to actually search through for that index and find it. Again, this type annotation here, this stuff is not necessary for this function to run, and it is not necessary for this function to run fast. Just good to see it. It's good for catching some types of errors, like you don't have to have the type annotations there. So this macro at assert, has anyone seen that before? New? Why you might want it? Anyone? No? Yeah, let's just do it. So again, if you got a question, it's at assert, it's a macro. We'll throw an assertion error if the condition is false. So what you do is you add assert, and then you put a predicate. And if it's false, then you can have text there if it's bad. Like, so what you should see is we're going to have this at assert not is empty priority queue. So if you try and run this thing with an empty priority queue, it's not going to work. You know, that's not well defined. I don't know if you should assert and throw an error, but the predicate, again, a function that evaluates the true or false by predicate is what I'm saying when I mean that, is that it's not is empty. So really another really useful one for arrays is you want to check whether anything's left in there. Is empty is false. Is empty for this guy is true. It's an empty array. So if you're modifying this array and you want to check whether it's run out, you might want to run is empty. For this one, you want to check not is empty, so that's fine. So if I did at assert for this, it's going to do nothing. But if I assert false, it's going to go assertion error is false, and I can go blah, blah. Assertion error, blah, blah. So you can put a bit of text in there. So this is like, if you're trying to write more robust code, this is the kind of thing you'll do. You'll put assertions in there just to check that this weird case, you've dealt with it, you're saying it's happening. I wouldn't, for me, I don't think I'd do an assertion error there. I do assertions more in tests than in actual code. I would do something like a try and catch statement. You'll see that later on too, or just a conditional. You go like, if is empty, write a message going, well, I can't sort this array. You gave me something stupid. Jump out of the program. Always good to think through those cases about what's going to break. Same as before, we had this naive sorting method, the naive implementation of a dictionary, I should say, and we didn't check whether we put the same key in twice. Same in here. You should put those little cases in there. So yeah, when you're scanning through, check you don't get the same key twice, because then you know your dictionary is broken. Okay, so again, you can improve this stuff by making sure that when you put things in the array, they're always sorted. Same thing again. It's amazing, you know, like sorting, priority queues, hand in hand. Yeah, but adding individuals is worse. So everything's going to get slow. So if you think about a heap as a black box, which is useful, if you just think about the complexity of the typical operations we said when we had this desiderata of like, we want this thing to act in this way. Big one is finding the maximum is order one. So you always know what's the biggest, or you always know which, depending on which way you built the priority queue, you always know the number one priority really fast. Deleting log n, insertions are log n, and updating a priority is log n. So unit 6, sorry, I got it wrong about where it'll be in your course, but you can think of it as a black box. You guys are going to do it for yourself. It's a little bit harder, but really useful. There's an implementation in data structures. I was saying about this useful package data structures. Using data structures, and there's, if you want to go, there's a bunch of types of things you might be interested in. You get an idea that this is like pretty intense, that there's like how much stuff is in here. Bunch of functions and a bunch of types. So Julia, you might have seen this syntax and not really completely twigged on it, that like a type is usually a capital letter and a function is usually these lowercase letters. So these guys over here, mutable binary min heap, will be a type. It's one of these structs I was talking about before. All these guys are functions. Whatever the hell comp3 non-leaf is, I don't know. That's just if you want to dig in and see what's there, looking through the documentation. But the one we're going to use is, there's this heap. This is how you would do a priority queue. You're going to do it yourself. You can also use this for sorting, because if you always know what the next highest priority is, it's really easy to do sorting, right? Like, it's almost painfully trivial. So what we're going to do is a particular type of heap called a binary min heap. Details don't matter. Not really going on about that. If you want to go and look, you can. What we got here, so just again to talk through this function. So heap sort, I hope everyone can remember exclamation mark means it's a hint from the writer of the code that it's going to modify the input. In this case, it's going to sort it in place. Going to take some array in, and we're going to make a binary min heap of L type A. So maybe I did say that one last time, I think. So if I've got an array AA, the L type of AA will be string. So it's an array of strings. The elementary type is a string. Really useful function for making things fast, because you can make sure the types of things going in and out of things are going to stay the same. That's one of the ways to make Julia fast. So we've got this binary min heap, and what we're going to do is we're just going to push stuff into it. So heap has the same operation like an array. You can push to it, but when you push, the heap data structure is set out in such a way that the top priority always stays accessible. It's always known which one's up the front. It's kind of like this idea of sorting the array, but a little bit more fancy. So this is really dead simple. We just push things into this heap. And then when we want to get it out, we want to sort, we just pop. So that's pop, the operation on is take the top element from the heap, take the highest priority element from the heap. So we just push it in and then we pop it out. We push it in, pop it out, and it's done. That's sorting done with a data structure. So all of the cleverness is hidden in the methods for push with a binary min heap. Somebody else has written all this code. Someone else has written this data structure. This looks trivial. We just push it in, pop it out. You can pop from an array too. It just takes the first element off. Same, but you know, so you could write this if you were careful and you wrote a special method about sorted arrays that push them in and make sure they go in the right spot. Heaps a much better way of doing that. So if we do that, sorted, done. Its priority is just based on that. It's really trivial, right? Like the data structure does all the work. This is this idea that like you can be clever with the types of things you're using and the way they're laid out, and it will do all the work for you. The algorithm becomes an implementation detail of a particular data structure. Big point. So this is called heap sort, and it's like good in a way. It's not what you do. So we're going to do a benchmark here. Let's see if there's some nastiness here. There is a little bit of nastiness here. We've got this GC enable equals false. This is horrible to have to do this. What this is like this is the detail of languages. Julia is a garbage collected language. I was showing you a little bit about pointers. One of these things you can do in Julia, allocate memory freely, whatever. I don't have to keep track of all these little shitty things I made. I just pop them out everywhere. If I call it inside a function and I never use it again, I never call that function again, I sort of want that memory to go away. I don't want to have to think about it. If I'm in a language like C, I have to manage my own memory. And it's one of these things that like, they're both high-level languages in the typology of programming languages, but there's like very high-level programming languages and lower-level programming, high-level programming languages. And those lower-level ones, you have to keep track of all the things you made. Otherwise, it eats your computer. You have no RAM. So this is one of these differences. It's kind of annoying. It's one of these ones that make languages like Python and Julia faster to develop in because there's less stuff you have to worry about. You can turn garbage collection off in Julia, though. That's what this one's doing to try and make the timing a little bit more deterministic. Bit nasty. If you see it, though, I feel like you should see it. There's this weird magic spell there. That's what that one's doing. Turning garbage collection on and off in terms of the heap sort bit to make the timings a little bit better. I think you could just be more careful about how you do this timing function. I'd probably rewrite this if I had the time. So time in milliseconds as we get up to 1 million. It's like, it's not bad, right? Like there's some of these weird spikes. Don't worry too much about that. That's just because the timing was done lazily. It's not careful. Again, use benchmark tools, use beat time if you actually want to be serious about timing. This isn't an indication of like what's really going on. It's more an indication of what was happening on that particular computer when it ran to make this plot. So maybe you can go back to the start and we can see that this heap sort, again, this stupid little function where you just push it in and then pop it out. and the magic of the data structure does all the work for you, is pretty good. Like if we compare the heap sort to built-in sort, they're both sort of scaling in this n log n way. But the coefficient is a little bit different. So heap sort is like twice as slow as the built-in sort, but good scaling. And for particular problems, mainly if you're doing discrete event simulation and you're doing a priority queue, heap is the way to go. It is the data structure because of all this editing that you're going to do on the fly, and you always need to know what to do next. Yeah, hopefully that's clear. So that's why I talked about data structures for so long. Data structures are, get the type of the data to do a lot of the work for you. Like if for your particular problem, if like say, I'm going to keep saying it, if you have a set, like if it says for the set of blah, check whether something exists or not, maybe you should be keeping that as a set. In this one, if you want to do sorting, having a data structure such that you always know what's the next biggest in the list and you can take it away. A heap is a really good way to do it. The difference in the coefficient is usually to do with memory. Like for these sort of asymptotics, allocating memory is slow. So when I'm popping things off a list, I'm changing the size of the object, I'm making a new array, all that memory stuff will do allocations. So if you're careful with the timing and careful with the program, the profiling, I should say, you'll see all this stuff. That will be the difference in implementation. And we'll see that with the next one. So the big takeaway, and I say it, I think it's really relevant for your homework and stuff. If you're trying to think about performance, think about the ways you can do stuff so that you only do it once or as few times as possible. With bubble sort, you're scanning over this array multiple times and you don't need to do it that many times. It's like, it should be obvious that you don't need to go through it again and again and again. The n squared times, there's some skips you can do. So either using a clever data structure or breaking the problem up into smaller problems so that you're not redoing work. That's how you make things fast. It's clever to make these things. So like if this is like not, you go, I could never come up with this. It's like, neither could I didn't come up with this. So next one we're going to talk about, Quicksort was Tony Hoare. I think that's the guy's name. He's a British computer scientist, and merge sort is none other than von Neumann. So he came up with that. So yeah, I don't feel bad if I couldn't come up with it either. Thinking about the performance stuff though is like, we can all do that. We can all analyze these things. We couldn't necessarily come up with them in the first place. And coming up with clever algorithms is very hard for particular problems. So it's more about seeing them and seeing what's going on. So I just check. So maybe you guys can tell me. So for your homework, implementing Quicksort, is that right? What do you have to actually implement? Ask anyone. Yeah, so this is all part of it. So I'm just going to brush over the details of Quicksort in particular. But this meta idea that it's like, break it up into small problems, solve those so you don't have to do it again. That's the whole idea of all these algorithms. Heap sort is the same. It's kind of the same thing. It's like I'm putting these things in. When I put these things in, I don't have to do it again. If I've already done it once, I don't need to come back and do it again. Yeah, I guess I should say quickly, like really quickly, about why heap sort is n log n, and it's to do with this insertion being log n, because you have to do it for every element. Do it n times. Each one of those is log n, so that total asymptotic complexity ends up being n log n. Then when you read these guys out, it's order 1. So that's why it's really fast, and that's why the scaling's n log n. It's really about building this data structure in the first place. And the slow bit would be the allocations you do here as you push these guys in, because it starts off as an empty heap and then you're putting things in there. So these differences about like whether you use quicksort or merge sort is about, can you do it in such a way that it doesn't allocate? Which is why quicksort wins in the end, because quicksort, but hopefully you guys see this when you're arguing about like, well, why is this one quicker and why is it better, blah, blah, blah. The practical detail about having to do allocations is a big deal. Okay, So we've got a bad implementation of merge sort. So key principle, sorting an array of n length, what merge sort does, so the big deal is that it will recursively, so we had recursion early on, it's going to call itself. And what it does, it breaks it up into small little arrays and then calls merge sort on them until they're tiny little arrays. I kind of think like I can talk a lot. I can show the animation on Wikipedia because it's like, it's really simple when you see it this way. So this is starting off at the back. There's just a little GIF. I don't know how you're supposed to pronounce that these days. Everyone says it differently. But the idea is when presented with an array, you're seeing the back recursion step here. We'll just wait for it to cycle back around. Wish I had a video. I could just skip to the start. I didn't think this through. What we're going to do is we take an array, we're going to bust it into bits, then bust it into bits again, and then bust it into bits again until we can't do it anymore. Then with all of these sub-arrays, we're going to sort them. And they're sorted already. So when we get two arrays, we can work out if I put them in front or behind when you're coming back down. That's basically the magic of doing merge sort. Talk through this guy. Again, this is all like Algorithms 101. There's a million explanations of this on the internet. Who'll do a better job than me. Read a lot, see, make sure you go through all this stuff and make sure you understand it. So we're going to go through just line by line for this guy. We've got my merge sort on data. Data should probably be a type array, but we won't force that issue. N is the length of the array. And if the length of the array equals 1, we just return, because the length array 1 array doesn't need to be sorted. We can just stop. It's already sorted. We've got this divide. P equals n divided by 2. Let's just do that. Have I got a decent array? 1, 2, 3, 4. Okay, so n equals length A. So that's 4. Just show you guys what this does. So that's just 2. So /div is this function. So if you looks like a little divide, /div, and press tab. If you want the help, oh, it's lots of stuff. So you can call div xy if you want this syntax. So the quotient from Euclidean integer division is what's going on here. Generally equivalent to a mathematical square without a fractional part. So this is basically just to deal with the case that the array is odd or even. That's why you do div. You just need to make it, we're going to split these arrays in half. Do you go low or go high? Make a choice, doesn't really matter. We just want to say, like, for the odd case, we want to put 3 in one and 2 in the other if it's 5. Then we're going to call my merge sort on the data from 1 to P. And we're going to call my merge sort on data from P plus 1 to N. So this is the bottom half and the top half. And the data new is a vector of L-type data on def-length data. So hopefully this syntax is okay for you guys. So AA from 1 to P. We'll pick up the first 2 elements. Remember, P was 2. So this is just make a subarray or make a vector. That's just the first 2. And because of Julia's array-based indexing, you go P plus 1 to N. That would be just split the array into those 2, and then we're going to call merge sort on those 2. Then the question is, they're recursively going to do this all the way down until they're 1, and then we're going to work out how we put them back together. That's why it's called merge sort. So you're going to keep recursively doing this. Okay, so now merge B and T are running indices for the top and bottom. So loop through the indices of the destination array. So if B is greater than the length of data bottom, it's finished. So that you're going to scoot through these subarrays. That's basically what it's saying. So you're going to go data new, I equals data top, blah, 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 blah. So this this is this intricate bit where it's basically like just look at it, go through it line by line yourself, I would say, and then just stare at this algorithm, stare at the animation, and you'll actually understand what it's doing. So it's basically recursively subdivide it, then put them back together such that the two subarrays are always sorted. That's what you're doing every time. I don't think there's anything too controversial there. I'd say, yeah, this is a good example of pulling it apart yourself. I don't think it's too edifying to do it to death. When we compare it, again, it's this asymptotic stuff. So this merge sort, if you time it, we did the timing before, built-in sort super fast, order of 0.1 of a second. This one's 0.6. If we do the plots, it's n log n. Again, n log n problem. So again, you're making sure you're not doing work twice, because once you've gotten down to this recursion and you're putting them back together, you don't have to do this rework. You're only ever sorting it once on the way out from the bottom of the recursion. Okay. So sort the bottom sublist, sort the top sublist, and then merge the data. So if you want to see why the computational time complexity of merge sort is n log n, there's three main actions carried out by merge sort. Sort the bottom sublist, sort the top sublist, and merge the data. Okay, this is one of those nice cases where there is actually a super generic theory for proving the complexity of these types of algorithms. I'm not going to say a hell of a lot of detail for it because it's, again, it goes into your homework and it's sort of the one for you to think through yourself. I think it's like super important to think through this stuff. But there's this thing called the master theorem. It's actually really quite recent. It's only 1980. It's this unifying idea for doing these kinds of recurrence relationships. So these kind of recurrence problems where you're going to recursively break the problem up and then put them back together. There's these different flavors of these algorithms, and it's actually possible to do the generic case more simply than it is a particular case. So you can use the master theorem to prove for all different types of sorting algorithms or all different types of algorithms that are based on recurrence and solving subproblems, what the complexity of the topic of the algorithm is going to be. The name's a bit off. I don't know why. Rivest is the guy in RSA. I'm pretty sure that's the guy. Yeah, so his name will come up when you look at cryptography and stuff. So it's based on, you have an algorithm that's based on a recurrence where it's like, I think we've got that in the notes. It's probably a bit clearer. So the time of this problem depends on coefficients of the subproblems and some other overhead for the problem. So the general form of this is like you're going to have coefficients A and B for size n and some function n. So for our problem in merge sort, we've got coefficient of 2. So the time for sorting the size is n, then t on is the time for each sublist. You can see that time for two merge order is running the whole length of the array does at once. So basically, the idea of using the master theorem, go through the proof yourself, is basically finding out what these coefficients are. So they're 2 and 2 for our problem. The general problem A and B. So you might have a different type of algorithmic problem where you can't split it in half. You can only split it into quarters, or you split it into some smaller list. And the size of A. So it's basically a bunch of these cases, and you can plug it in and work it out. That's the general proof. I'm not going to go through it because it would take too long and I'd do a bad job of it. But that's one way of analyzing the basis of these problems. You just have to work out what the coefficients are for your particular problem. So basically that's plug it into that, turn the crank, and you see that it's n log n. I won't say a lot. I'm just going to skip through because I think that's one to dwell on, pull it apart, do the problem yourself, think about the implementation details yourself. You'll get there. So quicksort is a similar kind of algorithm. But again, it's not, the problem with merge sort, if you're lazy, is you are making new arrays when you do the splits. So the big problem with this guy is it's not in place. So when I make subarrays, data bottom, data top, I'm actually making a new array. You don't want to be doing that. So the big advantage with quicksort, and again, you guys have seen through this, this is some pseudocode that looks a lot like Python syntax. Another divide and conquer one, but it's based on pointers. So you have a high index and a low index, and you just move those around. So rather than making new arrays, you just move some pointers. They're, you know, they'll get called pointers when you look at look into detail. Often when you read a description of quicksort, it'll say pointers, but just basically you can think of it as indices into the array. It's based on partitioning the problem and then pivoting it in. Okay. So you can go, one of the interesting things with quicksort is it actually has n squared. So it's the same as bubble sort in the worst possible case. Unlike merge sort and heap sort, they're both n log n, worst case, I hope I get that right. If you look at, I guess there's a zoo of sorting algorithms. So like if you look at Wikipedia page for quicksort, so sorting, I wanted to see the sorting zoo here. So there are a million of these guys, you know, because it's such a useful problem. It's simple, it's straightforward, lots of different implementations that come through. Quicksort's interesting in that the worst case complexity is actually n squared. But that's on pathological data. It's not a common case. So maybe, you know, this is one to think about. If you can think about like, what is the actual worst case for quicksort? What would make quicksort when you're going through your implementation? How do I break this so that it can actually hit n squared? Is that a common case or is that not so bad? Yeah, so n squared. The other thing is, in terms of practical requirements, is the memory complexity. So I've just been talking about time complexity because it's kind of easy, but I've been saying, you know, don't allocate as like a hint. Real world memory allocation is a big killer. Like you should think about the space complexity of your algorithms, like if they have to make memory to do something. So heap sort is bad in that way. Heap sort is saying order 1 for memory, but it depends on the implementation. Yeah, I'd say that's not, yeah. Anyway, you'll see with our implementation, that's not true at all. But a lot of these are based on a perfect implementation. So the best case complexity, average case complexity, worst case complexity. So even though the asymptotics are, you know, if you looked at merge sort, you'd go, it's actually better apart from memory. In practice, quicksort is generally faster for practical reasons. So I guess that's my educational point, is details matter for implementation. So even though something might be asymptotically the best, it's not actually the best. A million different sorting algorithms. Timsort is actually, I think that's what sorting in Python is, I would say. I think that's another one of these ones. So you will see these come up. There's a zoo. It's good to implement them. I guess if you're ever going to go for the leap code style software job, you need to memorize all these. I won't remember them. It's like they go straight out of my head as soon as I've done them. I don't know why they do that for those types of jobs. Yeah, see them. Analysis is like plug it into master theorem is the way to do it. You should try and understand the master theorem itself. Go through that. It surprises me that 1980, that seems really, really recent for analyzing the complexity in general of these algorithms. It's kind of nice if something's not too long ago. That was really fast. Takeaway point is think about how to do things once or as few times as possible. That's the trick to making algorithms fast. Okay, I don't have a heap of time, but talking on to tools. So nobody came and gave me, does anyone have a preference? Is anyone fighting Git? Anyone scared of Git? Anyone scared of command line? Anyone scared of IDEs? Is there anyone, do we have any votes for like which one you prefer to worry about first? Because you've got a week until the next lecture, I'm conscious of. Scared of all of it? Okay, that's fine. Git is scary. Yeah, okay. All right. I guess I can do that. Do you have a particular, do you want the overview of Git today or? Okay, that's fine. Let's do that then. I'll jump ahead. Yeah, okay, that's a good problem. That might be actually a good one to talk about the IDEs. It's like sometimes, yeah. You can do, yeah, maybe I guess, let's start with Git then. Okay, so history of Git is it was made by Linus Torvalds. So that should be a famous name. Some people are nodding their heads. He is the guy who started Linux. So he was building a big software project. I don't think he thought it was going to be as big as he thought it ended up being when he started. And this development process of this, exactly like I have my friend and they're doing work and I'm doing work. And we want to be able to keep track of everything that's going on and be able to share stuff and be able to build stuff. So like a big problem is like, I guess my thing I always think about for the motivation for Git is who does this? And everyone does this. So it's like when you're writing an assignment and you go like, it's the final version, and then you do an edit and you go, it's the final version, and it's final version 0.2. And is anyone doing that with their code at the moment? Where they're going like, this is the good one, I swear, and they'll change the name of the file, and then they'll have a couple of different versions of the name of the file. This is a very human thing to do. I've seen, I'll say it because it's funny, multi-billion-dollar companies that run on spreadsheets versioned like this. So everybody does this, right? It's terrible. It's hard though. It's actually a really hard problem. Like, how do you keep synchronized? How do you work with someone else? Even if you're working on your own, how do you keep track of the things you did over time? So again, this is solved by version control software. So there's been a lot of these over time. When I started, I think it was CVS was the first one I was using, Subversion, which was awful, particularly for this problem of sharing code. Like, it's actually really interesting in the design of Git compared to these other ones. So Subversion was like, there was a database that ran the master version, master. A lot of I will seem like an old person because I'll say master, and it's inbred and it's like deep in me. I struggle to say other things. A lot of people of color have gone like, oh, Jesus, that sounds like slavery. We don't want to call it master. Can you change it to something else? So older versions of Git will say the main branch is master. Now they tend to say main. So if you clone one off GitHub, main, that's all it is. Like, I'm just old and I struggle to change the words I use. I think that's a good change to change it because it's a bit of a yucky word. But the main branch of the code was run on a remote server. And you had this problem of lots of developers trying to get code to the same thing, and it was really slow. So there's a couple of weird things about Git that make it hard. If you're doing version control on your own, it's really kind of easy, right? Like, you can do this versioning by file. You just save a new version of the file. It's fine. Like, it's actually fine. You just have to keep notes with the changes that you made. And then that would be a perfectly fine, like, and you could go back through your list of notes and go like, oh, this version here points to this file. I can go and look at that file. If we're thinking about complexity, is that efficient in terms of the size of the files we're keeping? No. So what would be a better way you could do it to start with? Yeah. So you can keep, so one of the command line tools, I'll talk about this next time. If you go through, if you have two text files and you want to compare them line by line, there's a Unix command called diff. You'll get, this is a function running in Bash, if you're not familiar with this stuff. It's a little function like I can call Julia, I can call diff. I give it 2 text files that go through line by line and tell me the differences between those 2 files. So it runs an algorithm for doing the differences as well. What Git will do is it will call something very much like this diff and look through the files line by line. So I've changed one, I've changed another one, and I want to see what the differences are. And I'll only commit the differences. So I can reproduce based on differences. That's like an efficiency thing. It also leads to like one of these problems when people use Git is if they accidentally commit a binary. If I say about a binary, everyone happy? Like say if I'm writing my code and I also put next to it a JPEG and I commit that JPEG. If I may change 1 pixel on that JPEG, what happens to the file if I look through, pretend it's a text file and look through it line by line? Is that clear? Because it's not a text file, right? It's a JPEG. So if I'm thinking this thing's a text file, every line is going to be different, even though I change 1 pixel. So Git gets very confused and copies the whole thing again. And then saves it. So it makes it bigger and bigger and bigger. So if you're changing things like, don't commit things like binaries to Git. The design of Git is that. So you want to keep track of changes over time. That's pretty straightforward. You want to be able to revert changes to a previous point in time. So this is me. This is my day job. I go, oh, Paul, someone comes to me and goes, oh, Paul, can you fix this thing? I'm like, yeah, sure. And then commit, push, master. And that's even worse than the thing I was supposed to fix. Now everything's on fire. We need to go back to where it was before and redeploy that. So you want to keep this change log. So you want to track changes over time and you want to be able to do that. And you also want to be able to like, this is my good special version. You know, this one I know really, really works. And then I've got this crazy idea I want to try. I want to kind of sort of quarantine that change, do changes there, and then put it back in. That's one of the design things as well. I would also like, in case I drop my laptop in a bucket of water, it's going to be somewhere else. So I want to be able to remotely keep a track of this. And I also want to allow teams of people to work on a code base without treading on each other's toes. This, if version control was perfect, this is what it would do, all these things. So if you're thinking about, again, this is more like working as a professional software engineer, like what are the requirements of a version control system? I'd say if you can do all these things, it's fantastic. There are lots of versions of this, like, but I don't know, Git is the one that's one. Like it's like in the marketplace of ideas, Git is the #1. You'll see it everywhere. The really weird thing about Git, and the thing I think confuses people the most, is that it's distributed. Every Git repository is its own fine thing. It's like a distributed database in a way that you can copy this thing, your version, and then there's another version somewhere else, and they're 2 different things. And then the tricky bits are when you want to synchronize those 2 things, and that's where all the problems come from with how people drive Git. So, very broad overview of what Git is. Git is one thing, then there's GitHub. So they're 2 very different things. GitHub is for hosting Git repositories. Git is a program I can just run on my computer. Let's see. I don't know what I got on this computer. I hope I have something very embarrassing. Here. CD. There's a file called Cucumber. My son was writing a program. That's what that was. Okay, so I've got our course here. So this is a Git repository. So I can go Git. Let's see how old the version of Git on this computer is. Git version 2.25.1. So that's pretty old, I think. I can go Git status. Oh, sorry. That's terrible. The name of the course is too long, isn't it? So next to folder release. Okay. Okay. So this one is main. So a couple of things here. So I'm on branch main. Branch is confusing. That's this, it's a tree-like structure in Git. So the branch I'm on is main. This is like the special one. This is the source branch of all this stuff. And you see this funny thing that I'm up to date with origin main. So I have a remote version of this repo that I'm tracking on my local computer. So that one is actually the one that's hosted on GitHub. I think I'm logged in. So you all would have seen this one. There's the code here. There's the main branch. A couple of little branches coming off that, and everything's here. So I'm tracking this one remotely. So that's part of it. So I can see, if I say git log, I can see the history of all the changes that have happened in this repository. So remember I was saying about hash functions? That's how Git does the those little change logs. If we're going, this commit did this diff, this is what happened, all the way through. So what it actually does is it takes a hash of the diff, and that will go to a unique string. And that's what this little guy is. So I can jump to any point in history if I look through the logs, and I can say, oh, that's the change I wanted. I can go back and jump over here. This thing, in a very, very strange way, is very similar to the blockchain in Bitcoin in a weird way, that you take a hash and this cryptographic hash, and then you can jump around. Hash of the differences is kind of like what way blockchains work, which is really weird. But this is actually using a cryptographic hash as well. I don't know why. It uses SHA-1, it's called. But you can see Yoni's made some changes, 21st of July, blah, blah, blah. A whole bunch, we can go through all the history. So another thing that will bite beginners with Git, especially if you go out into the workforce, is don't put passwords in Git. Don't put any tokens in Git. It's very, very hard to get things out of Git once they've gone in there. Because of these diffs, it's keeping the whole history. You can actually do it, but it's a very big security risk, and it's one of these things that's really easy to do. If you have GitHub authentication tokens, I assume you're all doing it that way. Has everyone driven GitHub yet? Have they got? So maybe I can talk about this maybe now or maybe tomorrow. Did anyone, who's set up with a token? Who, put your show of hands. Yep, who used SSH? Yeah, use SSH. But GitHub token is just, it's a password GitHub generates for you. They used to let you do passwords yourself, but they decided it wasn't secure enough. So they took it away. It was about a year ago, they took it away. It's really easy for those little tokens, you know, because I'm an idiot. I'll save them in a text file somewhere. That accidentally ends up in a repo, and then you commit it. There will be a bunch of little robots swarming through GitHub, looking through repos for those sorts of things, AWS credentials, passwords. So be careful, just as a thing. It's very, very hard to get stuff out once it goes in. Basic idea is though, is this diff, hash, commit those changes. So you can go through all the history. This is kind of hard to look at though. I don't know, if you're really good command line person, you've got that sort of brain. You'll see lots of tools like this, depending on which system you are. Because I'm on Linux, I always use gitk. You see, it's not the best for looking through. This problem of working with, it was a bit of a mess early on. This problem of working with another person is, I don't want to tread on their toes. They might need to release stuff for the course. So you have the main branch where you keep doing that. What you can do is make a branch off of the main and then merge back in. So this is this pattern of what you do is you go, I'm working on here. I'm going to change this one file, or make it easy for yourself. The problems will come when you've got diffs on the same files, but to keep your life easy, what you can do is make a branch, make changes on your branch, and then merge it back in. There's a few more operations you need to worry about if both of you are changing the same files and things are changing, like if someone merges in before you. I'll go through that, but maybe not today because I've got like 3 minutes. So this is basically the working thing. And down here, you can actually see the diffs. Oh, that's a terrible one. Let's see. There's a good one. So there's like some sort of pedantic change in here where someone's like, oh, I want a space, like, because I didn't like that there wasn't a space. And you can see the line that was taken away and the line that was added in. Same here, there's like some call to a function that's changed. This was these negatives was the stuff that was taken away, and this was the stuff that was added in. A whole bunch of stuff. So that's the idea. So you've got these diffs, you can see the diffs, you can go to the commit. The other thing I'll talk about really quickly is, did I close that? That was silly. Oh no, it's there still. So GitHub. GitHub is this remote backup thing. It's this idea that it's this normal thing that happens with people is like the whole idea of the internet was this libertarian dream that we can have distributed things and people just share information. And then after 20 years, what we got is giant corporations like Google and Facebook, and 90% of the internet traffic goes through there. GitHub is the same. Git is this idea of it's this distributed system. We can share code and we can merge back in, and I can keep my version, you can keep your version, and we can share it. And then everyone who actually uses it goes, no, I just want a good version that's somewhere remote, and we all use that one. So GitHub is for hosting Git repositories, and the way most people use it will be for the good version is there. I clone from there to my local version, and then I push back up to that remote. This is the bit that makes Git hard, I would say, because if you're sharing homework with your friend, it's like, I can keep my version in control by getting changes from you, and keep my version in change. But if we're both trying to change this one over here, we tread on each other's toes and everything gets hard. GitHub is okay. There's patterns that will make it easy though. If you want to make a branch, like I was just saying, it's like clicky buttons. Like you can just go here. I can create a branch of Paul's test branch. It's like, oh, that branch doesn't exist. I can create this branch. So I can just click on that. Okay, there's a branch created there. So now I haven't actually pulled this. I haven't actually synced up my local copy of this repository with the remote one for a while. So I can git pull. So this is go to the internet, get all the changes that have happened since then. If I look at the logs now, Yoni's gone and done some magic elf stuff and changed some stuff. There would have been some new things. We can probably see that. So stuff about the homework that wasn't there because the last pull I had was like in July. So there's some new changes that have come. The other thing that would have come is Paul's test branch. So what I can do is I can go git, check out this branch, Paul's test branch. Now I'm here. Now I can go crazy. I can go into CD Markdown. And I can go, haha, RM, lecture, unit 2, git diff. Now all this stuff's gone. This whole lecture, this whole course. Now I'm going to push that to Yoni, and he's going to go, no. So I probably won't do this here now. So that's the diff. The diff was that I removed all the lectures, and that's fine. And in my local copy, that's fine. And I can commit this, keep the change. It's fine though, because this is just my local copy. The remote copy that we're building the lecture material off is fine. If I push it to there and try and merge it back into master, you should do a code review. So your friend should check whether this is okay or not and say, yes, no, we're going to do this. We're not going to let this through. So that's the pattern of working. I'll say a little bit more about it next lecture, but this is like hopefully a really quick thing. Again, getting the code should be pretty straightforward. You just click on code, SSH, Control-C. I can make a new, I haven't talked about Unix. I'm making a directory called temp stuff. I can go into this directory, cd temp stuff, git clone. So git clone is the thing. If I'm going to get a copy locally of this remote thing, I want to do git clone. And it will go here. So slow internet. It's actually a big Git repository because of all the pictures and stuff. So usually you don't want these pictures in your Git repository, but it's kind of easy for us to do it. So we did. Now, if I do ls, will show me what's in this directory. I've got another copy of this programming. Done. So I've got another copy of this thing. So these things, you can treat them as quite ephemeral and disposable, and you can do stupid things because it's this distributed system. The biggest thing with Git is it's very hard to lose things, but it's very easy to panic. One of the ones last year that was kind of funny was one of the students misnamed their repository and they couldn't find it on GitHub and they'd wondered where it had gone. Like, these sort of things happen to everybody. I've seen this. The biggest thing is like, don't panic, ask for help. I'm here, Yoni's here. Just put a question on Ed. Don't delete things. Like, if you've done something silly and you're panicking, just walk away from the computer and ask for help. If you don't touch anything, you can get nearly everything back. This problem I was saying about passwords, getting into Git repositories, and they're almost impossible to go away. It's the same for your mistakes, right? Like if you push something that you didn't mean to, it's very easy to go back to where you are if you know how to drive Git. It's just the learning curve for Git is a little bit complicated. So don't panic. That's basically the whole message. Okay, that was a very brief introduction to Git. I'll say a bit more next lecture. Thank you for your time, everyone.
Like